Good morning, everybody, or afternoon. It is a pleasure to be able to talk to many of you again about the work that we're doing at ZAP Surgical to bring down barriers to the wider dissemination of radiosurgery today through the ZAP-X Gyroscopic Radiosurgical technology. Many of you have kind of wondered why I'm just not riding into the sunset and kind of resting on the work that's been done in the past by myself and others and letting radiosurgery speak for itself. Well, it's really because there's a lot of work that's undone. And if one looks around the world today, it is seemingly evident that there are more than 2 million patients a year who would benefit from good brain and head and neck radiosurgery who don't have access to it today. And I repeat, 2 million patients who could benefit from radiosurgery, yet are only today 150,000 are getting such treatment. So I'm a great enthusiast for radiosurgery, as many of you know, and I consider it really one of the greatest triumphs of modern medicine, on par in most respects with checkpoint inhibitors and TAVR and you name what modern miracle there is. And yet radiosurgery is a well-kept secret and out of reach of more than 90% of the people in the world who would benefit from it. And to me, that's a major challenge to all of us. It was a major challenge to me, and that is the impetus for starting ZAP Surgical. I'm not alone in recognizing that. This nice article, I might add, published in Curious, of course, written by Jason Sheehan from University of Virginia, just looked at cobalt, gamma knife radiosurgery as a surrogate for all radiosurgery, brain, head, and neck, and looked around the world and tried to determine the access of different patient populations to gamma knife radiosurgery. And not surprisingly, in the United States and places like Japan, there seemed to be a fair amount of gamma knife radiosurgery availability. But when you go to much of the world where most of the population is, almost all of Asia, places like Africa, Central America, South America, you see that there's a huge discrepancy between what exists in the developing world and what exists in the wealthier parts of the world. So I'm not alone in understanding that there's a problem here with radiosurgical availability. In fact, it's not just a matter of money. Even in the United States, this article nicely demonstrates that while there's a fair amount of radiosurgery available in the United States, it's disproportionately located in urban areas with big medical centers, and there's virtually none in rural and many even suburban areas. This too is a barrier to the wider availability of radiosurgery to those 2 million plus patients a year who would clearly benefit from such world-class care. Why is this happening? Why is this miracle not more widely available? Well, I think it's a legacy of the existing delivery platforms. Clearly, the gamma knife has been the gold standard for 30, 40 years now, and it's hard to argue that it hasn't transformed the world of brain radiosurgery. It's accurate, it's highly conformal. However, it is really expensive to buy a gamma knife, not just acquire the device itself, but to build the infrastructure around it to support it, including especially a radiotherapy vault. And there's lots of regulatory apparatus that needs to be incorporated in a facility. Iris scanners every time you go in and out of the machine, being examined by the NRC. So, and I think that's why we don't have more gamma knives. Meanwhile, you have these, the Swiss Army knife, multi-purpose radiotherapy centers, and they've been around doing radiosurgery for 35 years. However, they're really designed to do a little of everything in the world of radiotherapy. Again, I liken them a Swiss Army knife, but a butcher doesn't use a Swiss Army knife, a wood carver doesn't use a Swiss Army knife, and neither does a surgeon. I mean, yes, if you have only one tool, it's good, but in a world of optimized treatments for specific anatomy, standard radiotherapy systems have not moved in that direction. They're not optimized for the targeting or dosimetry, as we'll show further. And they're pretty damn complex because they try to do everything. To be so flexible, you have to have lots of complexity, and that complexity takes a lot of extra training. So with these ideas in mind, with these being the barriers to, we think, the wider availability of radiosurgery, went about trying to create something new. And that something new is the ZAP-X. This is really the first of its kind, sort of self-shielded radiotherapy, radiosurgical device. Really, the operator literally sits in the room with the device, but it has been designed from the ground up, as you'll see, to be optimized for brain and head and neck radiosurgery, and only brain and neck radiosurgery. So what's striking for many, and because it is the first of its kind, is that this is vault-free, does not require radiotherapy vault. Why is that important? Well, I think it's important for financial reasons because vaults are expensive. And while $1 million vaults are possible in many places in the United States, 5, 10, even $15 million vaults in certain urban and suburban environments are not unheard of. And I know one locally where that's exactly what's going on. Meanwhile, the vaults kind of always constrain you to the basement, pretty much of the radiotherapy department. What happens if you have a big neuroscience center down the street or down in the suburban mall? What happens if you're a large, successful neurosurgery group and want to treat patients right next to your ambulatory surgery center? Well, historically, that wasn't what radiosurgery is about. But once you get rid of the vault, you can start thinking about where to position radiosurgery. And no longer does radiosurgery mandate that patients come to this big center of excellence. It means that center of excellence can go where the patients are. And so this is a concept drawing that's currently being built out in Loma Linda, but you can see you can build really sexy new facilities around the ZAP-X in a way that was never possible with therapeutic radiation equipment before. So this miracle of medicine doesn't have to be hidden away in the basement anymore. It can be front and center, building the brand of your local neuroscience center, for example. In fact, there's other facilities being designed right now here. Now the patient's being treated, nicely HIPAA compliant, but no matter, the brand of the product can shine very nicely, a broad light on the brand of your facility, your institution. And as I was already saying, that there's a couple of these going in major train centers, train stations in Japan, right behind behind a plate glass window is going to be a major pedestrian thoroughfare. Radiosurgery should be front and center in the world's consciousness of how to treat not only cancer, but many non-cancerous conditions, as we're going to be talking more about as well. What's also striking about the ZAP-X is it's cobalt-free, getting rid of all the regulatory apparatus that overlies traditional cobalt. You can see that there's 3 MV Linac, whose average energy approximates that of the cobalt photons, delivers a very high output of 1,500 rad per minute, 1,500 monitor units per minute, and just makes for very fast treatments without all of the financial and regulatory and ultimately the security problems that associated with cobalt. Now, unlike your traditional S-band linear accelerator that moves in a single plane using a single gantry, what we have here is dual link gimbals. And so a gimbal within a gimbal develops almost a gyroscopic-like pattern of crossfire. And what this means is we can get more crossfire using this mechanical design than is possible with any pre-existing radiotherapy or radiosurgical system. More crossfire equals tighter dosimetry. And so everything, as I go through this list of features, you'll see everything is grounded in better dosimetry, better targeting. Maybe not for the prostate, maybe not for the lung, because that's not what we treat, but in the brain. So this gyroscopic pattern leads to better, tighter dosimetry. And you do it without the time-consuming kind of the manual couch yaws that some of you are familiar with in traditional LINAC systems, including something like the Edge, which Varian says I created, but I did not. And so, as I just delineated, and I'll say it again, kind of in summary, we've developed from the ground up a platform optimized for brain and head and neck radiosurgery. At present, we have 260 plus non-coplanar beam angles. This greater measure of crossfire, more than 2 pi steradian, gives us steeper dose gradient, and dose gradient is really at the heart of all radiosurgery. As you can imagine, it also feeds right into eventually a world of arc-based treatments. 3 MB beam energy, well, it gives you less lateral scatter, again, gives you better dosimetry. The collimation system, which we'll show a little more in detail, does an amazing job of stopping almost all scatter off the primary target. And so all you're dealing with is just a beam, a tightly collimated beam of radiation emitted through this cylindrical collimation system. Far less scatter radiation than occurs with your standard multi-leaf collimator. In fact, 50 times less. And then lastly, this runs at a 45 centimeter SAD. Shorter SAD, significantly less penumbra. So more solid angle, beam optimized for brain radiosurgery, better collimation, shorter SAD. Everything from the ground up designed for the best possible dosimetry, which is especially relevant in your smallest targets where the world is headed. So here, this video is going to really basically walk through what I've just been talking about. Of course, dramatically lit because we intend to be cool. We're coming from the land of Tesla and Apple. It's got to be cool. Radiosurgery is built to be cool. But notice where the operator sits. Now you'll see how these dual link gimbals are going to give you all the crossfire. Patient goes into this machine. People think it's innately going to be claustrophobic. It is not. It is only a rare patient finds this claustrophobic because it opens up inside. There's your collimation system, 800 pounds of tungsten, which blocks almost all the primary scatter. And what you're left with is a finely emitted beam of radiation coming through one of these cylindrical collimation systems. And it's literally in a second or two, we can change apertures from 4 millimeters to 2.5 centimeters. Gives you far more flexibility than any pre-existing radiosurgical system with cylindrical collimation. There you have the image-to-image targeting system. We use DRs referenced against the CT scan, used from the CT scan, using real-time intrafraction positioning, much like the CyberKnife. You'll see many CyberKnife-like analogies. And here, in addition, we are able to move the table with 3 degrees of freedom. In aggregate, the entire system has 6 degrees of freedom. That makes us a robot-like device that allows us to position any tumor at any position within the workspace, deliver this kind of cross-fired radiation. So there you see the degrees of freedom on the gyroscopic mechanics, a linked gimbal within a gimbal. And this is what gives us all the degrees of crossfire. There's 260 different angles. More angles of crossfire gives you better dosimetry. Boldly going where I say no radiosurgical system has gone before. And so now we're shooting using a single aperture, but we can change apertures on the fly as well. And this point of crossfire is where we get, of course, the steepest dose gradient and what is the heart of all radiosurgery. Now you'll see not only do we know where the target is placed, but we also confirm the dose using this real-time dosimetry. For the first time ever, not only do we do calibration prior to treatment, but we can confirm the dose in real time, This is a safety feature that obviates some of the horrible complications that occurred in the past in radiosurgery. So here, this is what the modern radiosurgical facility looks like. It is there to build a brand for the whole field of radiosurgery. No longer is this a concept that hides in the patient, but it's front and center in the world of medical and surgical therapeutics. So let's talk a little more in detail about dosimetry, because that is really the heart of what we do. So this is a study done in water phantom at BBS, Neurological in Phoenix, which is our first and flagship site to date, where they looked at the dosimetry that's achievable with a 4mm collimation system in the ZAP-X, comparing it to other modalities. And so of course, the steeper the dose gradient, the better, because that's what gives you the ability to spare normal tissue in radiosurgery. And if you look at these series of curves from the 3 cardinal axes, axial, coronal, and sagittal, you can see that in every plane, the ZAP-X, which is the green sort of the dots, had the steepest dose gradient. Here it's about the same as the Gamma knife, but appreciably better than the CyberKnife, and would be appreciably better than your Linac-based systems, which we'll show you more. So what you see is, with this constellation of properties, the ZAP-X delivers the tightest dosimetry, the least penumbra of any radiosurgical system today, which is going to be increasingly important as we go forward and treat ever smaller targets. Just a couple of weeks ago, Ian Paddock from London, a renowned physicist, presented this particular data. Ian was asked by the NHS to look at all the different radiosurgical facilities in the UK and give feedback to them about the quality of treatment that they were delivering, using treatment planning and as a guide to the quality of the treatment they were delivering. And so he collected from a range of different centers, looking at Gamma knives and CyberKnives and a range of different variant and electrolinear accelerators, including tomotherapy. And then in this report showed one of these figures, which is a scatter plot, looking at the R50%, which is the 50% prescription isodose line divided by the target volume, which kind of is a correlate for both specificity and dose gradient, which I think is a very cool measure. And it's probably the single best measure of treatment quality of all. And what he found is that the Gamma knives, these little green triangles, were pretty darn good, because you'd like to have the smallest number along this axis. This is the target volume. Of course, that PTV influences the quality of your R50%, but the smaller the R50, the better. And so the Gamma knife, for example, was pretty much along this line. Linear accelerators were pretty much along this line. Some linear accelerator measurements were quite good. Some of these CyberKnives were even better than your standard linear accelerator, them being the pro. But he then plotted some ZAP-X treatment plans. And the ZAP-X were among the best of the best of this cohort of radiosurgical systems, although not yet treating in the NHS, but this is what will be a harbinger of the future, not in the NHS, but around the world. Meanwhile, he looked at some more, the last was metastasis. This is some more complex targets. Once again, the best of the best were the ZAP-X. So by building from the ground up a technology platform that incorporates optimal dose gradient as well as accurate targeting, allows one to create this type of dosimetry, which is now, I think, increasingly by objective measures understood to be best in class. Meanwhile, as Lars Lexell would always taught me, when the human brain is concerned, the tools cannot be too refined. Of course, he also said a fool with the finest tools is still a fool. So we're here to educate people as well. No matter if you compare VMAT, which many people think is a wonderful tool for treating brain metastasis, with what you can do with a ZAP-X, there's a huge difference in terms of integral dose and dose landing on normal tissue. And after all, is it not the role of radiosurgery to minimize the irradiation of normal tissue? And there we see, here we see in an axial plane, the same phenomenon. Too much radiation going to normal tissue with a VMAT, hardly anything with a ZAP-X. And here we have in the sagittal plane, the same phenomenon. So all these little attributes I've been talking about, give you better dosimetry, whether it be compared to VMAT, other LINACs, and really on par with the best of gamma knife radiosurgery today, but without the radioactive cobalt. Well, I'm going to delineate the key components of the ZAP-X here. This is how we achieve the dosimetry I've just defined. So there are two major rotational axes that define the device. We have this axial gantry, which is mounted to the floor. This is the stanchion that supports it, and it rotates around this axis, around the axial plane. Then we have an oblique axis. This is a big bearing in here that you really only see in cross-section, and this is the axis around which it rotates. These two axes intersect at a common isocenter, and that is where we get radiation crossfire. That is where we position the target of interest, and that's how we get the dosimetry I've just delineated. And then all these mechanical elements are rotated in this large treatment sphere, which support the treatment components, such as your linear accelerators, such as your wave guides, such as your KV imagers, such as your mega voltage detector. And we'll kind of go through these one by one. But they contain the radiation within this treatment sphere, allowing us to make this self-shielded. And there's also this rotary shell and door, all of which then contain the emitted radiation within this device, allowing the operator to sit right next to the patient treatment. And again, I repeat, the device opens up inside the apparatus, keeping this from being a claustrophobic experience. Those two rotational degrees are mated with a table that is 3 degrees of freedom, and then a collimation system with a fourth, yet another degree of freedom, giving us an aggregate of 6 degrees of freedom. So we like to refer to this as a radiosurgical robot. Radiosurgical robot, it really optimized for brain and head and neck radiosurgery. The KV imaging system, here's a KV source. There's a flat panel detector, rotates around the patient, and by using X-ray image-to-image correlation and the patient's original CT anatomy, we are able to know with sub-millimeter precision with sub-millimeter accuracy, where the tumor is located in space, and then to move the table to put that tumor at isocenter. The LINAC, once again, 3MV with this collimation system that is really best in class in terms of blocking almost all scatter radiation. And opposite is this MV dosimeter, which for the first time allows us to measure real-time transit dosimetry and confirm, we trust but verify that the dose being delivered is exactly what was planned. So one of the horrible little secrets of radiosurgery of the last 2 decades is that close to 1,000 patients that we know about have been treated in terrible ways, literally 100 being killed by this process. And that will never happen again with this new measure of security, enabling, we think, many more physicians to confidently treat with radiosurgery. And I can tell you, it's a dirty little secret of the industry how many patients have been hurt in the past. The UI, very simplified. The idea is to make radiosurgery accessible to everybody. This new UI UX allows literally one button, a click of a button. It is now possible to treat even complex targets with the best of dosimetry. Here, kind of an artificial target, but a hard to treat convex target. With a single click, the optimization algorithm tries to achieve the ideal 0 dose outside the target, and yet a highly conformal dose inside. And we can do that with a single click. We believe that this is a best-in-class treatment plan that's easiest to use and gives you the tightest possible conformality, taking advantage of all the different radiosurgical features that I've been describing here in terms of dose grading and flexibility. Uncluttered, simple, straightforward, and available to the world. That is kind of how we've tried to design the entire ZAP-X. Here's the collimation system again, a little more detail. You see this spinning disc has a series of apertures ranging from 4 to 25 millimeters. In a second, we can change aperture sizes and deliver best-in-class dosimetry with the steepest possible dose gradient. And this goes on repeatedly, allowing us to optimize aperture dimension as one of the primary variables of treatment and achieving the sort of dosimetry I've been alluding to. The KV imaging is derivative in many ways of this, what we did with the CyberKnife. From multiple angles throughout the entire procedure, we acquire real-time images from the amorphous silica panel that we have embedded inside the device, paired with the KV source. Real-time, these images are correlated against DRRs developed from the patient's CT scan prior to treatment. Within seconds, we can deliver sub-millimeter targeting accuracy, and this gives you frame-like precision without the need for, pins in the skull. So the virtue of this is you get away with using a frame, and then that, of course, enables fractionation. And fractionation, I think, makes a big difference for larger tumors, tumors in critical areas. And I think there's even evidence in the gamma knife world, reluctant evidence, I know for many, to say that fractionation does have value, a way to treat bigger metastases, bigger tumors. And at Stanford, for example, now when still in the CyberKnife world, many patients are obviating conventional fractionation for tumors like GBM and going simply to hypofractionated radiosurgery, which I believe is a win for patients who have limited life expectancy. So there's our MV imager. This is our, we think, a online QA patient safety breakthrough. It is possible now to record real time the dose of radiation being transmitted through the patient's head, but strikes this MV detector. This corroborates and what we believe is the truth from the calibration system. And never again will a faulty calibrating machine end up leading to horrible injury and overtreatment of patients, which, as I already alluded to, has led to death in some circumstances. So this device is a real-time device where the operator at any point finds a fault, can stop treatment, and confidently know that what has been delivered is exactly what they thought was delivered. So this is the technology that I've just gone through and I feel will be instrumental in allowing more than 2 million patients a year to be treated who currently don't have access to radiosurgery today. The business that's making this possible is headquartered in Silicon Valley in San Carlos, California. We were sprung up out of Varian originally, but we've been supported by Foxconn, the company that's probably making the electronics with which you're looking at this talk right now. So they're the largest manufacturer in the world, making most laptops and most iPhones and technology like that. And we also have other major funders which give us a secure financial base to live out the dream that we have shown you today. From a regulatory standpoint, we've had regulatory clearance in the United States now for almost 3 years. We've gotten clearance from the Japanese Shonin just several months back in the spring, and that's where we started to sell of recent. And we're deep into the throes right now of a major audit right now for the European regulators. And we're hoping soon to have our first ZAP-X in Europe. And we're also right now in the midst of a clinical trial inside China, being part of China's Green Pathway Accelerated Approval process. But there we see in China a potential market for many, many hundreds of thousands of patients every year to benefit from this type of procedure. So to date, we have 3 installations with more than a dozen coming. The Barrow Neurologic is the top and first machine that we installed here in the United States, and most people know the BNI. In China, we have Beijing 301, which is one of the more prominent hospitals in China, if not the world. And then lastly, we just began treating patients at MedStar Georgetown just last week. and we're excited to now be on the East Coast of the United States. So in summary, the ZAP-X is a new generation of radiosurgical technology designed to really make radiosurgery available to 2 million patients a year who unfortunately don't have access to radiosurgery. The virtues of this new approach are, number one, it's kind of null-free. It eliminates a lot of the cost, both financial and procedural, that are currently part of the world of radioactive cobalt and also linear accelerators. And by getting rid of the vault, we can now move out of the basement of radiotherapy departments and go to new locations where patients are, especially neuroscience patients. By getting rid of the cobalt, one no longer needs to worry about checking in with the NRC. One no longer needs to worry about, recharging the device every 5 years. One is really freed up from some of the traditional concerns attached to cobalt-60. And as I've said repeatedly, what we've built from the ground up has been optimized for best-in-class radiosurgery. And in the next slides, I'm going to show you why that's increasingly going to be important. But even in the world of oncology, where we're treating multiple small brain mets now, 10, 15, 20 brain mets, trying to do it fast, quickly, and try to do it with minimal penumbra, we have optimized that kind of platform. It is simplified, non-coplanar delivery, no couch kicks, best-in-class dosimetry, optimized LINAC beam energy for all tumors, but especially smaller tumors. We've optimized the collimation system so that there's almost no leakage off the primary target, and we've optimized the SAD. So from the ground up, this is intended to be a best-in-class technology and increasingly more affordable than any other. So while radiosurgery for oncology purposes has been transformational, I think, and really, as I implied, a revolution on par with checkpoint inhibitors and immunomodulation, I'm going to talk to you about something that I think is even more exciting in the future. And so the company, ZAP Surgical, is not only committed to showing you or bringing to you a ZAP-X that can treat oncology patients, but also exploring a new world of what we call radiomodulation. The idea that radiation isn't just for killing tumors, but it can also down-regulate brain circuits. And we see this already in cases like epilepsy and certainly trigeminal neuralgia, where high doses of radiation, sometimes almost instantaneously, can down-regulate a painful brain circuit or epilepsy. And so taking this concept and even some earlier clinical work, which I've talked about previously, we are trying to push the frontiers of radiomodulation as a company, opening up new vistas for radiosurgery. And here's one of our early victims to be. So in the world of addiction, we increasingly understand that there's a small area of the brain called the nucleus accumbens that underlies addictive behavior, whether it be opiates or alcohol or maybe even obesity. And so we are trying to understand exactly how radiation can downregulate not just any circuit, but especially in this case, the circuit underlies addiction. And so we've now created a model of addictive pigs. Really, they're alcoholics, and I'm going to show you kind of the model that we're working with right now. This is just a view into what the future is going to be like, albeit not quite the patients we're expecting. Well, here, this four-legged patient could be playing with toys, could go drink water, could eat some food, but there's also a pan of alcohol. And so these little pigs you see now are accessed after being addicted to alcohol and could literally do anything in their pen. But after drinking the equivalent of half a quart of a lot of alcohol in any one sitting, you can see how these pigs choose to spend their day. So here this pig, drunk as can be, doesn't want to play with anything, doesn't want to eat, doesn't want to drink water, just goes straight to the alcohol. This is what addictive behavior is all about. You've given up all your normal attributes of life, albeit for some of us it's not playing with a ball or drinking water alone, but this pig is giving up all the normal attributes of his life just to participate in this addictive behavior. And so he will be one of our early first test subjects. After this, we plan to look at monkeys, and then, and not too long in the future, start treating patients, because I think there's a huge, huge opportunity to transform the world of psychiatric disease for where our current treatments are so inadequate. So with that, I'm going to sort of thank you for listening, and I'm going to try to take questions one by one. I hope that most of what I've talked about is self-explanatory, but I welcome the opportunity to answer the questions that you posed. So bear with me as I go through this. So the first question is, when saying vault-free, you mean classical concrete bunker, but does the system need at least X-ray shielding, doesn't it? No, according to the IEC standards, literally no radiation protection is required at all. So as long as one is 1.5 meters from isocenter, 0 radiation protection is required. One gets nothing more than a general public dose of radiation. You don't even need to be badged. So no radiation protection is required according to the standards of most all countries. The question was right, does it use daily adaptation planning? And so perhaps this question kind of relates to head and neck radiosurgery, where you may, over time, want to modify your treatment field according to the target shrinkage. And to date, no, that is not part of the current product offering. Undoubtedly, it will be, but the technology does not have a cone beam CT built into it today. And so there really isn't a model for adapting target planning, which is really more conventional radiotherapy. This is really about radiosurgery, not conventional radiotherapy. So if daily adaptation is most useful is over 5, 6, 7 weeks of standard head and neck radiotherapy, where the tumor does shrink. Here, the typical 3 to 5 days of fractionation, which is more characteristic of radiosurgery, doesn't really fit well into this model of adaptive treatment planning. If the idea is that can we follow the target each and every day over successive days, well, that's very much characteristic of what image guidance provides. And of course, that is what all radiosurgery with image guidance does, as does the ZAP-X. So the question is, what immobilization is used? Well, the ZAP-X uses standard mask-based immobilization with which most people in radiotherapy industry, and especially those who use CyberKnife, are familiar. And it does a pretty good job of restricting movement. The purpose of the immobilization isn't to define where the target is, it's to limit movement so that the real-time KV imaging can take over and be the real vehicle by which targeting happens. Question is, what is the mechanical isocenter accuracy? It's amazing. This 15-ton apparatus moves around a mechanical isocenter with 0.2 millimeter accuracy. So it is extremely accurate. These large bearings, one largest of which is 3 meters in diameter, have amazing accuracy. Next question. I can confirm the insufficient access to radiosurgery, enormous need of ZAP-X in Eastern Europe. How does the ZAP-X influence the training requirements of the neurosurgeon using it as compared to other forms of radiosurgery? Well, it is the intent in building this technology to make it as intuitive as possible, to open up radiosurgery to more and more centers around the world. Training is a major impediment for most radiosurgical systems. In the world of the Gamma Knife, you require extra support to handle radioactive cobalt safely. Cobalt has its own requirement, but linear accelerator is extremely complex. I mean, they're marvelous, marvelous. I mean, you can treat anything from the toe to the head, to the lung, to the prostate with standard linear accelerators. But all that flexibility means a lot of complexity, and that complexity takes a lot of training. So by just focusing on the brain, head, and neck, the ZAP-X is much more simplified. And I tried to allude to that in describing the treatment planning, where literally a button allows you to treatment plan, a single click, and challenge you to do better. I mean, you could try to do better, and you'll quickly find out that you can't. And so that's how we have built this to enable, especially neurosurgeons in developing countries with requisite radiation oncology and physics support to treat their patients. There's been a question, could AI support and further optimizing and automating the ZAP-X functionality? Absolutely. I mean, we are going to be working with all our customers and mine the experience of the collective community so that someday in lesser and lesser developed parts of the world, whether it be Africa or South Asia, that allow almost any doctor to be able to treat their patient independently. It is a public health problem crying out to fix this problem of inadequate radiosurgery. And ZAP-X is committed to solving that by designing a easier to use system, and where useful, incorporating AI and optimizing functionality. Is it always a non-frame based treatment? Yes, the ZAP-X is designed to be always a non-frame based treatment. Now for a few frame zealots, it may occur that you'll see not a frame targeting system, but a pin-based immobilization system be adapted to the ZAP-X, but that's only in the works. But we believe that frame-based targeting will give you everything that you can get with a non-frame-based, a frameless system. You get everything you get with a frame-based system. But for a few zealots, we may make an exception, although it breaks my heart to do so. Is the ZAP-X conceived for AVM, benign skull-based tumors also? Or do we only brain mets? No, I showed a couple cases of at least on the dosimetry for skull-based tumors where you have much complex geometry. And I think you'll find that the conformality is best in class for skull-based tumors because of our optimized dosimetry. We have not treated any AVMs yet. There's no reason we can't. We're generally speaking, we're just still with our customers treating more and more difficult cases, each and every month. But of course, we'll be treating AVMs. We do not yet have all the capability built into the software that you'll find with, a Brain Lab or a CyberKnife or a Gamma Knife. But you're talking just in the next year and a half, you should expect all the most complex functionality that you can envision in any treatment planning system will be part of the ZAP-X. Today, we can treat with all 95% of that functionality. The last 5% is showing up increasingly, virtually every month. Another question about mobilization. Once again, patients are today immobilized entirely with mask-based mobilization, non-invasive mask removal. How long does approximately 3 lesions take to treat? Well, a single lesion depends on what you're treating. If you're treating, a complex skull-based lesion, it can take you 20 minutes or so, and understand that that's probably going to get faster because we can treat much faster and we're still only optimizing all these different features. But let's say a brain met, we can treat in 5 to 6 minutes. Pretty fast, and even that is going to get faster. So you're looking at time after time what we believe is going to be best in class in conformality, best in class speed, and really most accessible in terms of financial and complexity. I noticed the ZAP-X is in closed capsule. Are we able to sedate and monitor patients inside the ZAP-X? Yes, the ZAP-X is in a closed capsule. Until you get in it, you can't fully appreciate that it is not that claustrophobic and that you really don't need sedation, but there are occasionally patients for whom sedation is needed, absolutely, and the ZAP-X is designed not only for those patients, but also for children where general anesthesia may be required. So you can get general anesthesia monitoring equipment and and ventilator hoses in and out of this device. You can do any type of radiosurgery on any type of patients in this device. Someone asked, how many patients per day can this machine treat? Well, I mean, the most we've ever treated is, I think, to date, about 3 patients in a day, but we expect that patients are going to be, a dozen patients a day could be treated, if not more. There's no reason by running long shifts that someday we won't be running. And developing parts of the world where it is very important for throughput, where you won't be treating 15 or 20 patients a day. Nothing intrinsic to this technology means we can't treat lots and lots of patients. Treatment will be as fast or faster than any other device currently in the market today. Is real-time KV imaging obtained orthogonal? It is not orthogonal, neither is ExactTrack. So it's, yes, KV imaging is a little like ExactTrack. I like to say it's more like CyberKnife tracking, which was, of course, the original form of KV imaging. But yes, it's this projection KV imaging correlated against the CT DRRs is what drives the accuracy of this device. And it is, in that sense, comparable to ExactTrack. Good friend, John, too. Hello, John. We want to get us, okay. Okay, John, for those who don't know John, too, he's one of my heroes, so he's in Cincinnati. Yes, John, we'll be all over you. Okay, thanks, John. He says he wants one in Cincinnati. Whoever the sales team is, get there fast. Is MR fusion available with planning? Yes, of course. MR fusion is a standard part of all of radiosurgery treatment planning today, and we provide ready quality fusion between the treatment planning MR fusion, on which we do treatment planning MR, on which we do treatment planning with the CT, which is largely used for targeting. What is the length of the possible treatment volumes? How low in the neck can the ZAP-X go? The ZAP-X is designed to go to the base of the neck for the 95% male. So in America, 95% male in America. So if you're from the rest of the world, chances are we can comfortably treat almost everybody at the base of the neck. But some parts in America, in the middle of Nebraska, you get some American football player who weighs 350 pounds, and no, we're only going to get to the top of the neck. But for most parts of the world, we can get all the way to the base of the neck. Question about the emergency. Is there possible to evacuate the patient quickly? Yes. You can get in and out of this device much faster. The door drops almost instantaneously, but safely. And you can pull the patient table out literally in 15, 20 seconds, much faster than you can get in and out of any radiotherapy room, like a Gamma Knife or a linear accelerator room, which has a big door to open and close it. So we've thought about all this, and not a problem. It's in the weeds of this presentation, but assure you that safety has been built into every aspect of this device and ensured by both the FDA and all the world's regulatory bodies. Is there any benefit with vertical seating position versus horizontal laying down position? Well, that's a clever question, and I challenge someone to go out and build a radiosurgical device that's designed for vertical seating. Thought about that in building this machine. I figured that the problem with the vertical seating is to keep someone stable in space. When you're sitting, how do you ensure that people don't slouch? And as they slouch, they move. As they move, you have increasing degrees of inaccuracy. So this is why I chose to treat patients lying supine. But perhaps someday someone will prove me wrong. But the ZAP-X is very much a supine device, not a sitting procedure. Given the many, I guess, gantry angles with the ZAP, how does treatment time compare to arc-based procedures, say with Novalis X or Edge, especially for simple brain mets? Well, I mean, it's a good question. I mean, the ZAP-X, so, there are people who use the Edge or Novalis treatments to treat with VMAT. And so VMAT is very, very fast. So I don't think anybody can be faster than VMAT, but you give up in the process a huge integral dose to the intervening normal brain. making it very difficult to retreat these patients in the event of recurrent treatment. So if all you care about is speed and you're willing to do VMAT, well, no, the ZAP-X isn't as fast. But if you're then going to treat individual targets, as is true with Edge and HyperArc and Novalis TX, the ZAP-X is on par or faster than any of those treatments because we have 1,500 monitor units per minute dose output. And although it's a point and shoot machine today, it's already very fast, treating in 5 or 6 minutes a single isocenter. And in time, you're going to see this with ARC-based treatments getting much faster. So speed is one of the hallmarks of what we think that they're going to define this system. But not just speed, quality. So I want to emphasize quality and speed. Okay, so much of these other technologies is all about they try to optimize speed or they try to optimize quality. We want to give both speed and quality. Jody, how long does it take from installation to commissioning? Normally take 2 months from installation to commissioning, and I'm sure that'll be happening faster. If we can already do it in 2 months, I'm sure a year from now, it'll be down to a month or 6 weeks. What is the dose calculation algorithm? It is ray tracing today. I'm sure as we move more into head and neck, we will have Monte Carlo. Today is simply ray tracing. Can the ZAP-X machine be remotely operated? It cannot be, well, you need someone on site, you know. We're not yet to the point where patients can literally treat themselves, which maybe someday. But we do have tools now, remote tools, that allow surgeons and radiation oncologists to corroborate the patient positioning within the device and increasingly help with treatment planning. Is it possible for trigeminal neuralgia radiosurgery in the context of high doses? We've published on this to show that the quality, the dosimetry that you get with the ZAP-X is on par with the best gamma knives in the world. Read the article in Curious, and soon we expect to start treating patients with trigeminal neuralgia, and a couple centers that really spend a focus on it. As you can see, neuromodulation, including trigeminal neuralgia radiosurgery, is a big part of what we think this platform is designed for. Please compare capital costs between your system, gamma knife and LINAC-based in general terms. The ZAP-X is cheaper than any gamma knife and cheaper than any LINAC. I'm happy to have, you know, I'm not here to sell you one directly, but happy to have our salespeople talk to you about the cost of the cost of having a ZAP-X relative to these other devices. And I think this, I'll maybe take this last question. What about trigeminal neuralgia and tremor? Well, this platform has been built from the ground up to do radiomodulation, to do radiosurgery for neuromodulatory targets for functional disease. That is where we believe most radiosurgery is going to be done in 5 or 10 years. And the ZAP-X is a platform intended not just for today's oncology needs, but for where most radiosurgery is going to happen in the future to come. Well, I'm going to wrap up here. I think I've already spoken more than I intended. I really had enjoyed the chance to speak to so many of you, and delighted to hopefully chat again sometime, either in person or online. So everyone, be safe and stay well. Bye-bye now.